Jai Hind, welcome to the course Network Analysis and Synthesis, and we are discussing network synthesis of this course. So, in the last class, if we recapitulate, in the last class we discussed what is network synthesis. Basically, it deals with the problem of design and fabrication when input and output are known. Okay, then we also discussed what are the tools required to synthesize a network, and in this course we discussed what is polynomial and positive real function. So, for a network to be realized, it must satisfy the PR, it must be a PRF. Then we also discussed the methodology how to synthesize a network, and there are 4 methods. One is the removal pole at infinity, removal pole at origin, removal of conjugate poles, and removal of constants. So, we can take the help of these methods to just decompose a network function. And today we are going to discuss about the 2 elements single port network synthesis in a special form, basically known as the Foster and Cauer form. So, today we are going to discuss 2 elements type one port network. So, basically these are the Foster forms and the Cauer forms. So, Foster forms again have two forms. One is the series realization network, means component are in series and it is known as Foster first, and in the Foster second we have the parallel network analysis, elements are connected in parallel. So, series combination of elements and they are in the parallel. Then in the Cauer forms what we do, we just developed a ladder network. How we will do it, we will just discuss later on. So, again it has also 2 forms, one is the Cauer first form. So, in Cauer first form what we do the continued fraction expansion about infinity. What does it mean? It means we are looking for removal of pole at infinity, and in Cauer second we do the continued fraction expansion about origin. It means we remove the pole at origin. So, how we will do it? So, we for the Cauer first what we do, we just arrange the polynomials in the descending order and divide the numerator the denominator once we get the poles at the infinity. By the same way in the Cauer second form what we do, we arrange the polynomial in ascending order after having the poles at origins. So, in Cauer forms what we do, we just the technique is basically the division method, we apply the division method. Where in the Foster form what we do the partial fraction expansion. For the given function we do the partial fraction expansion. So, in Foster first form if the network or function is impedance function, then we go for the Foster first. If the network function is admittance function, then we go for the Foster second. Suppose the function is given and you have checked it is the impedance function of some say RL or RC, and you are required to get the Foster second. So, what we do, we just invert the impedance function to get the admittance, and then we carry out the partial fraction expansion. Okay. So, these are the some brief about the what we are going to do today. So, first we start with the 2 elements that is the L and C. So, if the function is given, and how will judge that the given function is LC, RL or RC. So, properties of these functions give a lot of help to distinguish whether it is LC, RL or RC. So, what are the properties? For say we are discussing the LC immittance function. So, what are the properties for the LC immittance? So, the first one is the ZLLC, means impedance of the LC function or admittance of the LC function is the ratio of even to odd or odd to even polynomials. Okay. First property. Then second, poles and zeros are simple and lie on the j omega axis. So, again I am drawing here, this is your S plane. Remember to mention S plane. This is your real S, this is your imaginary S. Okay. So, second line is First line is the ratio of odd to even polynomials. We can check with the degree of polynomials. Then second one, the poles and zeros are simple and lie on the j omega axis. So this is the j omega axis. So suppose here is something, then we have the pole, 0, 0 and so on. So for LC function, poles and 0 lie on the j omega axis. The third one is the poles and 0 alternate on the j omega axis. Suppose the 0 then pole, 0 and then pole and so on. The second is the highest power of the numerator and denominator polynomials must differ by 1. Then it can be the odd to even or even to odd polynomials, and the lowest power also differ by 1. And the fifth one is there must be a pole or 0 at the origin and infinity. So these are the some properties of the LC immitance function to check whether the given fs is the LC or not. Then if you are going for the Foster first or Foster second, then you have to cut. The technique is the partial fraction expansion. Okay. So given what we do, we just carry out the partial fraction expansion of the given fs. Okay. Look at here, this k0s, this term corresponds to removal of pole at origin. There are 4 methods. So this k0 by s corresponds to removal of pole at origin. If the function has pole at origin and if we remove, we will get k0 by s, this term. And this k infinity as this term we get when we remove a pole at infinity. Okay. And these terms are basically removal of conjugate imaginary poles. Okay. So for LC immitance function, we can have combination of all these 3: removal pole at origin, removal pole at infinity, and removal of conjugate imaginary poles. So out of 4 methods, what we discussed in the last class, in LC immitance we use only 3, not 4 1, that is the removal of constant. Okay. So this corresponds to removal of pole at origin, this corresponds to removal of pole at infinity, and these are the removal of conjugate imaginary poles. So if the given LC function is an impedance, suppose if fs is zs, then it can be realized in Foster first form. Okay. If the given function is fs is impedance function, then we can go for the Foster first. But if it is asked that find the Foster second, then given impedance function must be inverted and then we go for the partial fraction expansion. Okay. So this is the general partial fraction expansion for LC immitance function. Similarly, we can have the general structure of LC immitance function in Foster first. So this is, suppose this is a impedance, this impedance, so this k0 by s corresponds to a impedance, so it will be a capacitor, because if you remember x is equal to 1 by j omega c, replace j omega by s 1 by sc. So here basically value of the capacitance will be 1 by k0. So here c0 will be 1 by k0. We can look here, this and this. Okay. Look at here. So this is, this is impedance and we are going for the Foster first. So this is a inductor, j omega xl is equal to j omega l, and replace j omega by s. So we get sl. So this is inductor, and the inductor of inductance k infinity. So this will give the L infinity. Okay. Now these LC tanks, parallel LC tanks connected in series, depends upon the how many conjugate imaginary poles are there in your partial fraction expansion. Okay. If there are 3, then we have the 3 LC tanks. If there are 2, then we have the 2 LC tanks. If there is 1, then we will have 1 LC tank. So this is the general structure of LC impedance function, because we are discussing the Foster first. So we are talking about the impedance and admittance. So this is the general structure of your LC impedance function. So clear. Now come to the Foster second. So Foster second, if the given network function is admittance function, okay, and you are required to find the Foster form, then we go for the Foster second, okay. So and the partial fraction expansion is same, partial fraction k0 by s plus twice k1 s upon s1 s1 upon omega 1 square plus k infinity s. That partial fraction is same, either we are going for the Foster first or we are going for the Foster second. Structure will change. So there is that was the series realization, this is the parallel realization. So networks are connected in series and then they are in parallel. So this, if suppose if the given function is admittance function, so k0 by s, if it admittance, the k0 by s will be admittance, so it will be the inductor. So this way we can proceed, okay. How will get this? This is 1 by k2, 2k2 by omega 2s square, we discussed in the last class, we can discuss also here. So L0 represents inductor if YLC has pole at origin, okay, and C infinity represents a capacitor if YLC admittance, if LC function is admittance, then has a pole at infinity. So this term is corresponds to infinity, this corresponds to pole at origin, and this is the LC tank, conjugate imaginary poles. So we can, although in the last class we discussed, then we can have the simple problems just to synthesize the network in the first form of the LC impedance function. So this ZLC is given, it is a impedance function. We can see here, this is the power is 4, numerator, denominator 3. So even to odd, it is the ratio of even to odd polynomials, okay. And in a normal course, the function has equal number of poles and zeros, okay. If there are, suppose there are 4 zeros, then there must be a 4 poles. If there is deficiency, it means that pole exists at infinity, okay. So look at this function, we have the s is equal to 0, means we have the pole at origin. So we have the pole at origin. Pole at origin means we have the capacitor. So here we can have the capacitor C0, okay. We have the deficiency of pole because here the degree is 3, 4, so m minus 1 is 1, m minus n is equal to 1, it means one pole exists at infinity. So we have also pole at infinity. In the present case, we have the pole at infinity. It means we have also L infinity. So we can get K0, we can get the K infinity, okay. And we can see there is only one, complex conjugate imaginary poles. So there will be only one LC tank, okay. So there is a pole at origin, this is, and infinity because deficiency, and deficiency is that pole exists at infinity. So both series capacitor C0 corresponds to S is equal to 0 and inductor L infinity, that is corresponds to removable pole at infinity, will be present in this. So numerator polynomial power is higher than the denominator polynomial. So what we do, okay, in present case we cannot carry out the partial fraction expansion. So to carry out the partial fraction expansion, be careful, your function must be proper rational function, okay. So what we do, just divide the numerator polynomial by the denominator polynomial, first step. Then we can get this, thus this 2s plus k0 by s plus k1. If we take now take the partial fraction expansion. Okay, k0 by s plus k1 by s plus 2 k star, that is the conjugate of this k1 s minus j2. Okay, so we have this. So this is the removal of pole at infinity. So this is inductor. We have get we have got one inductor by just one division. So we have got the inductor, then we have carried out the partial fraction expansion. Now we have to find the value of k0, k1, and k1 star is the conjugate of k1. Okay. So simple. S is equal to 0, we can get the k0 9 by 2. Simple partial fraction expansion and finding the poles residual by Heaviside expansion theorem. So just put s is equal to 0 in this, we get this, and we can get k1 is equal to this. So this is the real quantity 15 by 4. So k1 star will be nothing but it will also be 15 by 4. So straight away we can write 15 by 4. So this is the partial fraction expansion of this ZLC. Okay. So this is your removal of pole at infinity, means it is a inductor. This is a capacitor. Capacitor of capacity 9 by 2. So it is 2 by 9. Okay. So how will do this? Suppose I am writing here. If you remember in the last class, I am again doing here. No need to remember anything. This is your SL and this is your 1 by SC. Okay, and then find the ZLC. So it is SL into 1 by SC divided by SL plus SC, and try to convert in this format 2k1s upon s square by 4. Try to convert this. So it is coming 1 by cs. So this ss is cancelled out. So it is coming. You can check it. Just I am writing the direct expression for this ZLC. It is 1 by c into s upon s plus one by LC. Okay. S square by 1 plus LC. S square upon 1 by LC. So now we can see here twice k1s. So 1 by cs. So c1 is equal to 1 by 2 k1. Okay, and s square plus 4 is equal to s square plus 1 by LC. So 1 by LC is 4. So this way we can get the value of C1 and L1. So just if you are not remembering this expression for C1 and L1, very simple. Just connect a LC in parallel, find the equivalent impedance, and try to compare with this twice k1s upon s square by 4. We can get this. So we have C1 is 2 by 15 and L1 is 15 by 8. So this we can see here 2 by n f. This is the removal of pole at origin. We get the capacitor when the functioning impedance. Twice s removal of pole at infinity, we get inductor of inductance twice Henry, and this is a LC tank, because in the original expression we have the only one conjugate imaginary poles. Okay. Now come to the Foster second form for the same numerical. So ZLC is equal to s square plus 1 s square per 9 s into s square 4. So impedance function is given and you are required to find the admittance, Foster second, means Foster second is realized for admittance function. So, what we will do, just invert this impedance and to get the admittance. So, we get this YLC is equal to, just invert this, okay, and look at here, the function is a proper rational, okay, carry out the partial fraction expansion, carry out the partial fraction expansion, okay. So, we can see here in this problem it is also a ratio of odd to even, okay. There is no pole at origin, there is no pole at infinity, okay. In this admittance function there is 0 at origin and there is 0 at infinity, but the method is removal of pole at infinity and removal pole at origin. So, what we do, we carry out the third method, that is the removal of conjugate imaginary poles. So, there are two. So, the if general structure will be LC in series, L1 C1 in series, L2 C2 in series, and they are in parallel. The structure of, just by looking the expression we can get what should be the structure of this Foster second for this function. Look at here, by this function only we are removing this conjugate imaginary poles. So, we will get the 2 L1 C1 in series, L1 C1 in series, L2 C2 in series, and they are in parallel. So, carry out the partial fraction expansion. The technique is, for Foster's technique is the partial fraction expansion. Before the carrying out the partial fraction expansion, you must ensure that the given function is a proper rational function. Without ensuring and you are carrying out the partial fraction expansion, you are committing some mistakes. So, be careful. So, we can find the K1, K2, and if we find the L1 1 by 2 K1 and C1 by 2 K1 by omega n square, and this is the structure of the Foster second. So, L1 C1 in series, L2 C2 in series, and they are in parallel. So, we are carrying the removal of conjugate imaginary poles, there are 2, so there will be 2, okay. So, very simple, very simple, very simple. For the Foster first or Foster second, check whether the given function is impedance or admittance. If it is the impedance and you are required to find the Foster's first, go straightway. So, but before carrying out the partial fraction expansion, check whether the given function has proper rational or not. So, technique in Foster is partial fraction expansion, and we are doing the removal of pole at origin, removal of pole at infinity, removal of conjugate imaginary poles. There are 3 methods, okay. Now, come to the another one, that is the Cauer. Cauer is the ladder network development, okay. And if you go for the Cauer first, then we carry out the division method here, where in the Foster we carry out the partial fraction expansion, here we carry out the division method, that is the continued fraction expansion. Okay, no problem, understood. So, degree of numerator and denominator must differ by 1, because it is the ratio of odd to even, even to odd. Therefore, there is always a pole or 0 at infinity, depending upon the which one is higher. So, each time we remove a pole, remove an inductor or capacitor, depending upon whether the function is impedance or admittance. So, if the ZS is given, if the impedance function is given, and you are required to find the Cauer first, just carry out the continued fraction expansion. Before carrying out the continued fraction expansion, arrange the polynomial in descending order, and then go for the division. So, we get Z1S, Y2, Z3, Y4 and Z4. So, this is the structure of your Cauer first. This is inductor L1, then we have the C1, L2, C2. So, series are inductor and shunt arm capacitor for core first. If the ZS function being expanded has no pole at infinity, then it has a 0 there, but the method is remove the pole at origin or infinity. So what we will do, if the function has 0 at infinity, we just invert to get the pole at infinity. Did you get my point or not? If the given function has 0 at infinity and we are looking for the pole at infinity, what we will do is just invert and proceed further. So it's seen that the nature of the first element of the network is fixed by the nature of the ZS at s is equal to infinity. The first element is inductor series arm if it has a 0 at s is equal to infinity, and then first element is a capacitor. Okay. If the given function fs is an impedance, then the first quotient must be impedance, on the other hand is a admittance. Chord second, lowest degree of numerator and denominator polynomials में LC admittance function must differ by unity. So it then follows that there must be a 0 or pole at origin. So removing successive pole at s is equal to 0, continued fraction expansion about origin. Okay, that is chord second. Continued fraction expansion about infinity, that is chord first. So what we do generally to get the chord second, we arrange the polynomials in ascending order and then carry out the division. These are the, so removing successive pole at s is equal to gives a network in second chord form. In order to remove the pole, first arrange both numerator and denominator in the ascending order of s. That is in this way. So before carrying out the division, we must arrange the polynomials in ascending order. Okay. So this we can get 1 by C1s, 1 by L2. So this is the general form of a chord second. Okay. And this is, so first arm, this is the series arm, this is the shunt arm. So in case of the chord second, we have the capacitor in series arm, and the shunt arm we have the inductor. So this is the general structure of chord second. Since the first term of the expansion is impedance, then the second term must be admittance, because we are inverting. Now come to here, numericals. So theory will be cleared by carrying out a large number of numericals. Okay. So here synthesize the network in the chord first form of the LC impedance. Here we can see here, just convert into it. This is given in the pole 0 form. This is given in the pole 0 form. We have to convert into the polynomials and then arrange the polynomials in descending order and try to divide. Carry out the simple division. S is q plus 4s, 2s4, write down, try to eliminate the first element. So here we put the 2s, we can get the 2s to the power 4. So this element, if this is impedance, so this is impedance. Okay, so this is Z1. Now we have the inverted 12s square plus 18 and we get this. So first element will be impedance, second will be admittance, impedance, admittance, and so on till the remainder becomes 0. Okay, we carry out the continued fraction expansion till we get the remainder 0. This is the simple. The technique is go for the pole at infinity. We have here, then arrange the polynomials in descending order and then carry out the continued fraction expansion. Then we can fabricate the chord first form. So this is the chord first form. So twice h, this is twice s, SL. If you convert the, if you remember, transform impedance, resistor, inductor and capacitor converted from time domain to S domain. So for the inductor we get the SL. So there is twice Henry. This is a admittance. This is admittance. So 1 by SC is the impedance. If we invert it, we get the SC, as admittance will be SC. So what will be the value of the capacitor? It will be 1 by 12. 1 by 12 into C is 1 by 12, okay, and so this is the structure of your core first. Core second, same numerical core second. So what we do, just carry out the division. We can carry out the ZLC. So 4s plus SQ, then 18 plus 20 S square plus S twice S to the power 4. Try to remove this, so it will be 9 by 2s. Okay, we get the 18 here, then we get 9 by 2s square. So here we get 31, 25, 20 into 2, that is 40 minus and 31. So 31 by 2 s square plus twice s to the power 4. Okay, then this 4s plus SQ. So we can carry out. So here it is coming 8 by 31. 8 by 31 S. Okay, then we get this 4s. Simple division. Then 16 by 31 SQ. Then we get here 15 by 31 SQ. Then try to divide this 31 by 2 s square plus twice s4. Okay, then try to divide by 961 by 30s, just to get 31 by 2. If we multiply this with this, we get this. So this is coming 31 by 2 s square, cancel, then twice s to the power 4, then 15 by 31 SQ. So what we do, this will be 15 by this is your 62s, this is 31s, so this is 62s. We get 15 by 31s cube. So this, now the remainder becomes 0. So start with here. We started with the impedance function, so this is Z1. This is Z1 means it is capacitor. So it is capacitor of capacitance 2 by 9 F. Clear? Then this is your Y2. So this is your Y2, means it is capacitor, then we have the inductor. So it is 31 by 8 Henry. Then this is your Z3. So this is your C3. So C3 is coming 30 by 961 F. And this is your Y4. So capacitor, inductor, and then we have the L4. So L4 is coming 62 by 15. Okay. Now we have the general structure of core. First start with here. We have the capacitor, then we have the inductor, capacitor, C1, L2, C3, C1, L2, C3, then we have the L4, I can put the value here. So, it is 2 by 9 farad. Then we have the 31 by 8 Henry. So, this is 31 by 8 and 8 Henry, and this C3 is your 30 by 961. So, this is 30 by 961 farad, and this is your 62 by 15 Henry. Okay. So, this is the general procedure to carry out the synthesis for LC immitance function in all the 4 forms: core first, core second, Foster first, Foster second. Now come to the another element considering RL or RC. Okay, we consider the LC. So, LC is the separate entity. Okay, we can easily distinguish that the given function is LC immitance function because it is the ratio of odd to even polynomials, and the poles and zeros lie on the j omega axis. So, these two lines clearly distinguish the LC from the other RL or RC. Now, the other one is RL impedance or RC admittance. Okay. If you go for the property of RC impedance, it is the same as LC impedance. So, both the property of RL impedance, RC admittance will be carried out simultaneously. Look at here, all the poles and zeros are simple and located on the negative real axis. So, similarly, just draw here, because if the function is given in form of your Fs, neither Zs nor Ys, then you have to first find whether which type of function it is. So, property will help you. This is, and this is S plane. Never forget to mention this. If you have the S plane, then you have the imaginary S and real S. Without mentioning S plane, we have no meaning of this. Okay, simple XY. Okay, so all poles and zeros are simple and located on negative real axis. Poles and zeros alternate on the negative real axis. They alternate. The singularity nearest to or at origin is a 0. This you must remember this one. This is very important. And the singularity nearest to infinity is a pole because it alternates on the negative real axis. So, first coming the 0, then the last will be the pole. The residuals of poles of Z RLS are real and negative. You can check. For the given function, Fs is given, carry out the partial fraction expansion and look at the poles residuals. It is coming real and negative. And this the line written in the bracket is very helpful to carry out the partial fraction expansion. So, the residuals of the poles are real and negative. Then how can carry out the partial fraction expansion? Then we go for this. Divide by S on the both sides and then carry out the partial fraction expansion, find the coefficient, then after that multiply with S. We will do we explain this with the help of the numerical. Then slope is positive for this and this. ZRL infinity is greater than ZRL 0, given function. Just to remove the infinity by infinity, 0 by 0 in the determinant, and then put S tends to infinity, we will get the some values, put S tends to 0, get some value, and if on comparing we get ZRL is greater than ZRL infinity is greater than ZRL 0 or YRC. So, properties of RL impedance and RC admittance are same, and if we just invert it, just in reverse order we go, we can get the property of RC impedance or RL impedance. Okay, poles and zeros are simple and located on negative real axis. Poles and zero alternate on the negative real axis. Singularity nearest to or at origin is a pole in case of RC impedance or RL admittance. Singularity nearest to infinity is a 0. Okay, the residuals of poles of ZRC are real and positive. Slope this and this one means ZRC 0 is greater than ZRC infinity and so on. So, this is the partial fraction expansion of RL impedance or RC admittance. Okay. So, whatever ZRL we have checked, it is ZRL, then divide by S on the both sides. So, here now the K0, K1, K2 up to Ki they are real and positive. If you carry out the partial fraction of expansion of this ZRL by S, this K0, K1, K2 all are the real and positive. So, just be careful. This line is very important, numerical point of view. For the theory of writing the property you can write 1 to 7, but to carry out the numericals this line is very important. What the students do, just they carry out the partial fraction and they getting the coefficients real and negative, then they write down the Foster first of this function is not possible, because they have carry out the partial fraction expansion of ZRL. They have not carried out the partial fraction expansion of ZRL upon S. So be careful. These are the simple I explained here, because this RL, R or SL, it will coming in a Foster first. If you are going for the Foster first, this component will come. Look at here, in LC in place of R it was C, so replace C by R, we get this. So simple ZRL SL into R, this is the parallel combination of this. So this is the impedance, this. So try to find this one, this. Then this is the for the, if you are carrying out the Foster first, this component will come, this structure will come, then try to find the ZRL. If we are going for the Foster second, so we have to admittance. So this RL in series, then take this. So this and this, they are the very important. Similarly for the RC, this is the ZRC and this is the YRC. So if you are not remembering the value of the coefficients K1, K2 in the partial fraction expansion, just do some rough work and try to find this, and then comparing you can get the value of R1 and L1. If you are going for the Foster first, that is the impedance, or R1 C1 if you are going for the Foster second, that is the YRC. Here is a numerical. Look at the numerical, the nature of the numerical. Synthesize the network in the Foster forms which are given by function Fs. So first we will go for the checking of this function. Okay. So we can just look at poles and zeros are real and simple and lie on the negative real axis. First line. Then singularity nearest to origin is a 0. Here 0 means zeros at S is equal to -1 and -3, and poles at S is equal to -2 and -4. So singularity means pole or either pole or 0. Nearest to origin is a 0. Okay. If you draw it on the S plane, so first here this is -1, so here you will get the 0, then the pole 0 pole minus 1, then we have the minus 2, then we have the minus 3, then we have the minus 4. So, poles and zeros lie on the negative real axis and they alternate, okay. And the singularity nearest to origin is a 0. Residual poles are real and negative. If we carry out the partial fraction expansion of this, the residuals are real and negative, and f infinity is greater than f 0. So, if these four properties are satisfied, then given fs is either ZRL or YRC. It clear? So, this in place of fs we can write ZRL or YRC. Suppose now look at the problem. Synthesize the network in Foster forms. Nothing mentioned. Foster first or Foster second, nothing more, not mentioned. RL or RC, not mentioned. So, a group of students, what will do? They will make the Foster first of ZRL and the Foster second of RC, ZRL and YRC. So, this is the ZRL and YRC. So, if nothing is mentioned, some group of students will make Foster first of ZRL and Foster second of ZRC. Okay. Some group of students, what they will do? They make the Foster first of ZRL, and by inverting this function we make it admittance, they can make the YRL. So, some group of students make the Foster forms of RL network. Okay. Some group of students will make the Foster and second of RC. Suppose this is the admittance, so they can make the Foster second. Now, invert this, we get the ZRC, and we can make the Foster first. So, all three groups of students have done answer correct, have given the correct answers, because nothing mentioned. If it is mentioned of synthesize the network in the Foster forms of RL network, then they have to make the ZRL and then invert it to get the Foster second. So, so here the residuals of poles are real and negative. So, what we will do? Just divide by s of this. Now, we have checked this fs, this fs is nothing but this is ZRL or YRC. I have considered ZRL. So, I am going for the Foster first. So, for the Foster first, what we do? Have to carry out the continued the partial fraction expansion. So, if we carry out the partial fraction of expansion from this one, we will get the poles residual real and negative. So, what we do? Just divide by s on the both sides, and now we can carry out the partial fraction expansion. So, we can get this, we can get this, we can get this. Okay, clear? So, Foster first contain as partial fraction expansion. So, now carrying out, now can find the value of K0, K1 and K2, you can find the this. So, this is the structure of, here we can see there are the two poles on the negative real axis, two poles. Okay. So, and the pole at the origin. So, we have the two this and one this, and this is the structure of. So, this is the Foster second, simple carrying out the Foster partial fraction expansion. This is the second Foster of RL. So, this is the impedance. To get the Foster second, function must be admittance. So, inverted it and carry out the partial fraction expansion, find the value, and then this is the structure. So, for this what you have to do? Just take R SL in series, find the admittance and compare with this factor, and we get the value of R1C1. ZRC. So, we can go for the Foster first, ZRC. So, function we have inverted to get the Foster first, Cauer first and Cauer second. And in the polynomial, since descending order, try to find the continued fraction expansion, and this we can get the. So, R L1 C1 in case of LC. So, L1 R1, L1 R2, L3 R4, L5 and so on. Similarly, for the Cauer second we have this. The function has 0 at origin. Look at here, the function has 0 at origin. So, to get the pole at origin, we invert the function. So, invert the function to get the pole at origin, and then arrange the polynomial at ascending order, carry out the division. Once we have inverted the original function, then if we get the structure of this cosecant, the first element will be missing. So, we start with the second one, y2. Be careful, we will start with y2 because we have the inverted the original function to get the pole at origin. Be careful. So, there are some just these are some tricks. So, first element is missing, we start with the second one, and so on. So, I am stopping here, and there are some special problems related to synthesis. So, I will take one more class. On the next time we will discuss the RC impedance and RL impedance and try to summarize, and we just discuss about some techniques how we will do the problems more efficiently in the examination. I will check. So, that we will do in the next class. So, thank you very much. Jai Hind.